In session number 10, we will be discussing about cell representation. So what is cell representation? You know what I mean by cell. Cell is nothing but it is a setup wherein you convert your chemical energy into electrical energy, or by utilizing electrical energy into chemical energy, which consists of three components: an electrode, that is two electrodes, anode and cathode, as well as an electrolyte. So what do you mean by cell representation? Cell representation is this much, as the name itself tells. You are representing a cell through some fixed rules wherein you can observe the representation and tell which is anode, which is cathode, is salt bridge present or not, what is the concentration of the electrolyte taken, etc. things. That is, from this thing, that is representation, you can draw the information, every information of your cell. So such a representation is called as your cell representation. It represents everything about your cell. Just like your Aadhaar card, wherein you can have all the informations about you. So cell representation is in the same thing, a format wherein you can know everything about a cell. So let us see how to write this cell representation generally first, followed by I will be taking an example of Daniell cell that we have discussed in your session 9. So Daniell cell representation is very important, as well as you should also know how to write the cell representation if the reaction or something is given, some information is given by the question. So as a result, cell representation is very important. Sometimes you get 1 mark question to write the cell representation of Daniell cell also. So first let us know, in a cell, that is electrochemical cell, we know that left hand side is always your oxidation happening and it is anode. So anode is written on left hand side itself. On the right hand side, cathode is present and it is negatively charged, positively charged, and you know reduction is happening. So representation is written on the right hand side itself. So you know, I think this LOAN, L-O-A-N. In the previous session I have told you LOAN. What do you mean by LOAN? L is left, oxidation, anode, negative. So left side will be writing the left side itself, and the right side, cathode, will be written on the right side itself. We know that on the left side oxidation is happening, that is your metal solid is undergoing oxidation, that is Mn plus, it is becoming Mn plus aqueous. So M, metal rod, which is dipped in an electrolytic solution wherein metal rod itself loses electrons. So metal solid, metal ion, that is which has been loosed electrons and entered into aqueous medium. This has been separated by a slash like this, that is a line like this. Metal, respective metal which acts as an anode here, and its ion that is present in your aqueous medium after oxidation. You can observe metal here, it is in zero oxidation state. It has lost electrons, so positively charged. So there is an oxidation in the first portion of your cell. The right side is your cathode, so it undergoes reduction and it is positively charged. So right side itself I have to write down. So what is happening on the cathode? Reduction is happening, that is Mn plus aqueous, that is the ions that is present in your electrolytic solution grab the electrons from the electrode. As a result, they get converted into, they reduced into metal. I think you could understand. Reduction is happening. So you will be separating by a line. Reduction is Mn plus to M, that is zero oxidation state here, which means that it is reduction. Increase in oxidation number, oxidation. Reduction in oxidation number, reduction. So as a result, here left hand side oxidation is happening, right hand side reduction. You can observe this. Reduction, oxidation. Left hand side, right hand side. So which is the metal and the metal ion, you have to replace in this positions. We know that this contains a salt bridge, and salt bridge is represented by a double line like this. A double line represent, it is a salt bridge. It is a salt bridge. Salt bridge. Along with this, you have to also mention if you know, you have to mention the concentration of this electrolytic solution itself. That is, if this Mn plus, we know if it is 1 molar, say 1 molar, you have to also mention this one. If it is a gas, you also have to mention the pressure of that gas in terms of atmosphere. Say for example, I will take your Daniell cell. Take your Daniell cell. Daniell cell. So what is present on the left hand side? In your session 9 we have seen that left hand side is zinc rod dipped in zinc sulfate solution. Right side it is copper rod dipped in copper sulfate solution. So Zn rod dipped in Zn2 plus solution, aqueous, followed by a double line. What do you mean by a double line? Salt bridge. Yes, we have used a double salt bridge in your Daniell cell, salt bridge. And right hand side you have dipped the copper rod in copper sulfate solution, but copper ions are getting reduced, as a result Cu2 plus aqueous to Cu, that is salt. So say for example your zinc sulfate is say 1 molar and your copper sulfate electrolytes you have taken, it is 1 molar. Think that it is 1 molar each. So I have to mention it here. It is 1 molar. Here also I have to mention it as 1 molar. 1 molar. So from this representation I can completely set up a Daniell cell. How? What is present on the left hand side? It is lone. Left side it is an anode. So zinc acts as an anode. What is happening? Oxidation is happening and it is negatively charged. I can set up your oxidation half cell. Right hand side, reduction half cell. We know that copper is present dipped in copper sulfate solution. What is happening? Reduction. As a result it becomes right hand side, that is your reduction half cell. And by knowing this representation you can observe that there is a salt bridge, so I have to use a salt bridge. So like this, from a cell representation, if I draw all the informations about a cell and I am completely able to set up that cell, such a representation is called as your cell representation. But remember, this is very important for your 1 mark question, that is write down the cell representation of your Daniell cell. This is electrode potential. Let us take a container. I will be illustrating what do you mean by this electrode potential. Well, let us take a container. This container has an electrolyte, into which I have dipped a metal rod, Think that this metal rod, this is dipped in an electrolytic solution. So when a metal is dipped in an electrolytic solution, think that in this situation, the metal is losing some electrons. That is, the oxidation is happening in this half cell. Let us think that oxidation is happening in this cell. That is, M metal solid, it is undergoing oxidation. That is, it is becoming Mn plus N electrons. So M is your metal, solid metal rod which you have dipped. It is losing some electrons. Losing of electrons is nothing but oxidation. So this metal rod, when dipped in this electrolytic solution, think that it is undergoing oxidation. That is, Mn plus is been coming out of the solution here, Mn plus, and electrons are on the electrode like this, on the electrode. Now you can observe that the electrode itself has become a negatively charged rod. That is, since the electrons are crowded over the metal rod, you can observe that the electrons, the electrons which are present on the electrode has made this electrode negatively charged. The electrode itself has become negatively charged. Since the Mn plus ions are coming into the electrolyte, the positively charged ions have been increased in this electrolytic solution. That is, I can depict is like this. That is, if this is an electrode, these are negatively charged things, electrons, and the electrolytic solution has been increased by your positive charge like this. That is, this is negatively charged things and it is surrounded by a positively charged ions. That is nothing but this is your electrons and these are your cations that has entered your electrolytic solution. Now, due to this charge separation, there is a potential difference developed. Due to charge separation. That is, this rod is negatively charged due to rich in electrons and the electrolytic solution has rich cations. As a result, the electrolyte is, you can think it as positively charged. As a result, due to charge separations, due to different charges, there is a potential difference developed. This potential difference developed between the electrode and the electrolyte is called as your electrode potential. It is called as your electrode potential. So, potential difference is nothing but it is the difference in energy carried by the charge. There are two types of charges here, a positive charge and a negative charge. So, they have different energies carried by each other, which are separated at two different points in a circuit. So, there is a charge separation here. So, a positive charge and a negative charge separation is present. As a result, there is a difference in energy. This difference in energy is called as your potential difference. So, this potential difference developed between the electrode and the electrolyte, and an electrode is dipped in an electrolyte is called as your electrode potential. It is called as your electrode potential. So, how can I define electrode potential? Simple, is nothing but it is the potential difference developed when an electrode is dipped in an electrolyte at equilibrium. Remember, it should be at equilibrium. That is, this reaction which you have taken here, it should be in equilibrium. That is, the metal ions lose electrons and the metal atoms lose electrons and they have to enter your metal electrolytic solution, and the backward direction reaction, that is, they have to accept electrons and they get deposited over the metal atom. So, at this condition, if the electrode, that is the potential difference is developed, such a potential difference is called as your electrode potential. So, how can I define this electrode potential as? Electrode potential can be now defined as, it is the potential difference developed between an electrode and an electrolytic solution at equilibrium. So, it is the potential difference developed between an electrode and an electrolyte when you dip an electrode into an electrolyte at equilibrium. Very important, it should be at equilibrium. That is, say for example, if you take this one, this is an oxidation reaction happening. That is, when you dip an electrode into a electrolytic solution, the rod loses electrons. As a result, this is the case, M metal solid, equilibrium, Mn plus, they enter aqueous solution, plus n number of electrons. So, it should be at equilibrium. Very important word. The measurement of this electrode potential, that is the electrode potential difference developed, it should be at equilibrium. So, it is the potential difference. What is potential difference? It is the difference in energy carried by the charges. There are two types of charges here. Charges separated at two different points in a circuit. That is, they are separated by each other. That is, this is negatively charged, the electrolytic solution is positively charged. So, as a result, there is a difference in potential developed. That difference in potential is called as your electrode potential, and that should be measured at equilibrium. That if you measure this difference in potential, such a potential difference is called as your electrode potential. There are two types of electrode potentials. You can observe that. In this case, what we have studied, it is oxidation reaction happening. That is, the metal rod when dipped into the electrolytic solution, it is losing electrons. As a result, this is called as, that is, in this case, the case I have taken, it is called as oxidation potential. Oxidation potential. Oxidation potential. You call it as oxidation potential. So, I will be taking another illustration. The same thing, you take a container, you have an electrolytic solution, dip a rod into it. So, this is your metal rod, this is your electrolyte. Think that in this illustration, if you dip a metal rod into this electrolytic solution, the reduction is happening. That is, the metal ions that is present in your electrolytic solution, they grab the electrons from the metal rod and they get reduced. That is, Mn plus in electrolytic solution, they grab the electrons. These electrons come from your electrode, that is metal rod. They grab the electrons from the metal rod. As a result, they undergo reduction. Think this case is happening. In your first case, we have seen that the metal rod, atoms of metal rod itself loses electrons. Here, the metal ions from the electrode, they are taking out of the electrons and they are getting reduced like this. So that is your oxidation reaction happening. In this illustration, think that it is reduction happening. So now what happens? The metal ion which is here in your electrolytic solution, they are grabbing electrons from the electrode, which means that this metal rod is now in loss of electrons. As a result, I can take this metal rod to be positively charged. Now the metal rod becomes positively charged. That is because the metal rod is giving electrons to these metal ions. As well, the metal ions that is present here, they undergo reduction into metal, solid metal, and they get deposited over your metal rods. Like this, they get deposited. They go and they get deposited over this metal rod. As a result, what happens in this electrolytic solution, the negative ions that is present is increasing. Negative ions means the other ion that is present along with this Mn plus. Say for example, if you take zinc sulfate, zinc ions have been reduced means sulfate ions are present. Sulfate ions are nothing but negatively charged ions, they get increased. As a result, what happens? The negative charge around the electrode increases in the electrolyte like this. That is, I can illustrate this as a metal rod. It is positively charged now. It is positively charged, around which you have a negative charge. Negative charge. Again, it is a potential difference developed here. So that is called as electrode potential. So the rod looks like this now. It is positive because it has lost electrons. The electrolytic solutions, ions, negatively charged ions have been increased. So as a result, it becomes negatively charged. So again, there is a potential difference developed, which is called as your electrode potential. Again, you can observe that here reduction is happening, hence it is called as reduction potential. Reduction potential. Reduction potential. So you can observe here in this first illustration, you can observe that the oxidation is happening. There is a charge separation between the electrode and the electrolytic solution. Since oxidation is happening, the potential difference developed is called as oxidation potential. In the second illustration, reduction is happening when you dip a metal rod in your electrolyte. So since there is a charge separation, a potential difference is developed. Since reduction is happening, it is called as reduction potential. So there are two types of potentials, electrode potentials, that is your oxidation potential and your reduction potential. Simply generally talking about electrode potential, it is the potential difference developed between the electrode and the electrolyte at equilibrium is called as your electrode potential. How it is developed? I have shown you two instances wherein one of the thing oxidation happens, the metal rod becomes negatively charged, the electrolyte becomes positively rich charges. The other thing, the oxidation thing, wherein the metal ions will grab the electrons from the electrode becomes positively charged, then the ions in the electrolyte becomes negatively charged, increase in negatively charged. Hence, in both the cases, there is an increase in, that is, there is a charge separation, hence potential differences developed. In this case, you call it as oxidation potential. In this case, you call it as reduction potentials. This electrode potential depends upon mainly on three factors. So what are those factors if I take? It depends upon nature of electrode and electrolyte. Electrode and electrolyte. Secondly, it depends on concentration of electrolyte. Thirdly, it depends on It depends on temperature. It depends on temperature. So electrode potential depends upon these three factors. If these three factors, that is, if your concentration of electrolyte and temperature is kept constant, it's kept standard. Say, if the concentration of electrolyte is 1 molar, or if it is a gas, say if it is a gas, if it is 1 atmosphere, if it is a gas, you have to take into consideration of your 1 atmosphere. So if the concentration of electrolyte is say 1 molar, or if it is a gas, if it is 1 atmosphere, and if temperature is at its standard temperature, say 298 Kelvin, that is 25 degree Celsius. So if I make these two conditions, that is your concentration of electrolyte and temperature constant, you call these electrode potential as standard electrode potential. You call it as standard electrode potential. Electrode potential. Potential. So what do you mean by standard electrode potential? Very simple. It is the potential difference developed between the electrode and the electrolyte at equilibrium. Also, at standard conditions like concentration of electrolyte is 1 molar, if it is a gas it is 1 atmosphere, and the temperature at 298 Kelvin, if you measure the electrode potential, that electrode potential is called as your standard electrode potential. Electrode potential is symbolized by just E. It is symbolized by E, while standard electrode potential has been deferred by electrode potential by E naught. E naught. E naught means standard electrode potential. E means it is your electrode potential. So remembering once again, electrode potential is the potential difference developed between the electrode and the electrolyte at equilibrium. The same thing here, but the condition should be standard. What are those two conditions? Remember, electrolytic concentration should be 1 molar and temperature should be 298 Kelvin. So at this temperature and at this concentration, if you measure the electrode potential, they are called as standard electrode potential. Again, there are two types of standard electrode potential, that is standard reduction potential, standard oxidation potential. So there are two types. One is standard oxidation potential, and standard reduction potential. I think you know what do you mean by oxidation potential and reduction potential. Very simple. When you dip a rod in a electrolytic solution, if oxidation is happening, the potential difference developed is called as oxidation potential. When you dip a rod in electrolytic solution, if reduction is happening, the electrode potential developed is called as reduction potential. If they are at their standard conditions, they are called as standard oxidation potential, standard reduction potential. You symbolize it by SOP and SRP. Standard oxidation potential, standard reduction potential.